Hello everyone, my name is Tong Liang En. Today I will present my project, Federated Learning under Heterogeneity. In this project, I compare FedProx, FedAsync, and two Staleness-Aware Extensions based on Section 2C and Section 2D. The main focus is to study how different federal learning methods behave when clients have a statistical heterogeneity, different latency, and dropout behavior. One important challenge in this federal learning is that clients are usually not homogenized. The first type is statistical heterogeneity, means that different clients may have different data distribution, which lead to non-ID data. The second type is system heterogeneity, means that client may have different computation speed, communication latency, or even dropout behavior. Therefore, this project has three goals. First, I compare synchronized and asynchronized federal learning method. Second, I study how dropout and staleness affect convergence and accuracy. Third, I imply Staleness-Aware Extension based on Section 2C and Section 2D and analyze their behavior in this experiment. In the experiment, I compare five methods. The average is the basic synchronized baseline. FedProx extension, and by adding the proximal term to the federal average to handle the heterogeneous client, and FedAsync is a synchronized method where the server doesn't wait for all clients. Instead, it updates the global model whenever a client update return. I also imply two extensions. Section 2C adjusts the server aggregation weight based on the staleness, and Section 2D uses the predict embedding target in the embedding space for contractive learning. For the dataset, I use synthetic MNIST and FedMist. The model architecture is an MLP encoder followed by a linear classifier. The last hiding layer is used as embedding for contractive learning. FedAverage and FedProx are synchronized methods, so their local training is usually described by local epoch. In contrast, FedAsync and the two extensions are implied in an asynchronized setting. So I control the local computation using a fixed number of local mini-batch updates. To make the comparison fair, I convert local epoch into approximately equivalent number of mini-batch updates. The goal is not to make every client have exactly the same computation, but to align the local training budget across different methods as much as possible. In addition, a synchronized method requires a latency model. I use latency model to generate the completion time of each client, and then compute staleness based on when the update returns to the server. This allows us to observe how each method handles stale updates. And this slide shows the basic idea of FedAsync. Unlike FedAverage or FedProx, FedAsync doesn't need to wait for all select clients to finish training. Whenever a client update return, the server can immediately use the local model to update the global model. The update can be viewed as a weight average between the current global model and the return client model. The weighting factor can be adjusted by staleness function. If an update is more stale, it can be assigned a smaller influence. The advantage of FedAsync is better system efficiency because the server is not blocked by the slowest client. However, the drawback is that stale update may make the global model update direction less stable, which can affect the convergence. The main idea of Section 2C is to directly consider staleness during server aggregation. In other words, the server doesn't treat all return client update as equivalent important. Instead, it adjusts the aggregation weight based on how stale each update is. When client update is relatively fresh, means that the staleness is small. It receives a large aggregation weight. On the other hand, if an update is already stale, it means that the client training based on an older global model, so the server reduces its influence. In addition, extremely stale update can be rejected directly. This prevents very old local model from causing too much disturbance to the global model. And the idea of Section 2D is to handle staleness from the perspective of client-side cognitive learning, since the global model received by client may already be outdated directly using the stale global embedding as a target may not reflect the current state of global model. Therefore, Section 2D predict a current global embedding based on the past change of the global embedding. Then it combines the stale global embedding and the predict embedding to form a target embedding. Intuitively, when the delay is small, the stale global embedding can still represent the current stale reasonably well. So the client can rely more on it. When the delay is large, the client rely more on the predict target to compensate for the effect of staleness. And this slide is the difference between Section 2C and Section 2D in contractive learning, and both methods add the contractive regularization term in the embedding space, and both use the previous local embedding as the negative target. And this main difference is positive target. Section 2C directly use the stale global embedding as the positive target. So the local embedding is put toward the global embedding received by the client. And Section 2D use a predict global embedding target. So the local embedding is encouraged to move toward and estimate current global state instead of only the stale one. In addition, the quantitative weight is adjusted according to staleness. When an update becomes more stale, the influence of the contractive term is reduced, so that contractive regulation doesn't overly distribute the supervised task. And this slide shows the accuracy comparison. Here, I mainly observe the performance of different methods under different dataset and dropout setting. Overall, FedProx remains a strong and stable synchronized baseline FedAsync can avoid waiting for a slow client in a synchronized setting, but a more sensitive to stale update. Therefore, under some high dropout or some high latency variation setting, its performance becomes less stable. Section 2C and Section 2D can improve over FedAsync in some cases, which suggests that staleness-aware waiting or embedding level correction may help the asynchronous learning. However, the improvement is not consistent across all datasets, so that the result still requires further analysis. And this slide shows the loss comparison. Loss help us to observe convergence stability, not only the final accuracy. From the result, we can see that when a dropout or a stale update become more significant, the loss of a synchronized method may become less stable. This is reasonable because the server may receive local update training from the older global model, which can cause the oscillation in the global update direction. Section 2C reduces the aggregation weight of stale update, while Section 2D tries to correct stale information using a predict embedding target. This design can reduce influence of stale update in some cases, but the current results show that their improvements still depend on the dataset and the experimental setting. And finally, I want to discuss why Section 2D may behave similar to Section 2C in this experiment. Also, Section 2D introduced a predict embedding target. If this predict target is very close to the stale global embedding, then the contractive direction provided by Section 2D becomes very similar to that of Section 2C. In other words, the effectiveness of the Section 2D depend on whether the prediction can provide information that is meaningfully different from the stale embedding. If the predict target doesn't significantly change their positive direction, then the improvement may not be obvious. To summarize, FedProx remains a stable synchronized baseline in current experiment. FedAsync has advantage of not waiting for slow climb, but it is more sensitive to a stale update. The staleness-aware design of the Section 2C and Section 2D can reduce the influence of stale update in some cases, but effectiveness of Section 2D depends on whether the predict embedding target provide a useful correction direction. And it's my project presentation.